Hello, everybody, and welcome. Turn that light on so you can see me a little bit better. Oh, blew out the light bulb. So, good morning, Mr. D and Mr. Dossie, or good afternoon. So, this is the Q&A session for practice number 4. And so with that being said, I was going to ask if there were any questions based upon practice number 4, which was on more advanced series and parallel circuits. Was everybody able to find the video that I posted on Wednesday for practice number 4? Let me send that out. Okay, good. Okay. First question, what is impedance matching? Impedance matching, I'm going to try to type this out, is where we match the internal resistance to the load resistance. Okay? So, in an impedance match situation, and I'm about to show it on the board, we are driving some sort of element. Okay? Let's say it could be a light bulb. Okay? And a light bulb is going to have a certain resistance to it. Okay? Or let's say I'm driving a speaker. Okay? And our speaker would have a given resistance. Okay? And what you find out is that you want to give the maximum power from your system to the load, okay, to whatever you're driving. You want to have as little wasted power as possible, okay? So to do that, if you can get the internal impedance to match the external or the load impedance, you're better off. So let's look at an example. So I'm going to take this and we're going to go to the whiteboard here. And based upon other people's comments, I'm going to try to do it from the right-hand side. So let's say, let me get this up a little bit just so we can see it. So if our load is equal to 10 ohms, okay? Here, let me back this up a little bit so we can see that a little bit easier. Okay. And let's say we've got a battery here. Okay. And this is our driving circuit. So we know that this is 10 ohms. How do I get the maximum power here? Okay. And just to make life simple, we're going to make this a 20 volt battery. Okay. And this is R. Okay. Now, I know for a fact that power is equal to VI. It's also equal to V squared over R. And it's also equal to I squared R. Correct? So, if I wanted to figure out what's the way to get the maximum power here, okay, we'll call it P10. That's going to be equal to I squared times 10 ohms. Right? All right. Now, if I know that I is equal to V divided by R equivalent, that means that it's equal to 20 volts divided by R plus 10 ohms. Correct? And what you're trying to do is you're trying to solve for the R that will give you the maximum amount. Okay? And what you'll find out is that as the R goes up, this I squared goes down, which makes perfect sense. Okay? And it's 1 over R plus 10. And what ends up happening is that it hits a maximum value where R equals 10 ohms. So in that particular case, my power of 10 is equal to 20 volts. I'm gonna do the I squared R. 20 volts, 10 ohms plus 10 ohms squared times 10 ohms. And so that becomes 20 over 20, which is 1 amp squared times 10 ohms. It comes out to 10 watts. Okay? That's for the maximum. But let's say I used a 5 ohm resistor instead. If I did that, that's 20 volts. Or let's just say I had 0 internal resistance. So that's divided by 10 squared times 10 ohms. Okay? Hold on a second. I apologize. I really messed that one up because, see, I squared in that case would actually be lower. So did that answer your questions? So that was an example of how to do that. The next question was, are snap circuits good practice? Yes, they are. Keep in mind the number of different resistances are less than if you made your own. Okay, so a snap circuit is a real easy way to put together a circuit. Okay, you're going to have a voltage source, you're going to have some sort of resistances. You can even have it driving an LED light. You can also have it driving a motor. You can also have it driving just a regular incandescent light bulb. Okay. You can also use your multimeter. Remember, we talked about multimeters. So you can use your multimeter and you can measure the resistances and you can measure the resistance. And you can also measure the voltages of individual components. Well, you need to know how to use breadboards. Yes. Here's the thing. Even though breadboards are not specifically called out in the rules, odds are if you go to enough competitions, somebody's going to use a breadboard. Okay. Now you'll notice, and I've got this up right now, here is the national website's webpage for Circuit Lab, okay? And what you will notice here is that they have a lot of different things. They've got the score check sheet, they've got problem solving, learning TV, they've got the Science Olympiad TV page, okay? They've got all of our PowerPoints and all of the homework generator, etc. But if you look here, it's also got circuit breadboard resistors. So if I click on that, it talks about how a circuit or breadboard works. And the way a circuit or breadboard works is if you have usually a 22 gauge wire, it is connected on these 5 are all connected independently. So you don't have to tie them together. They're just naturally connected. Okay. You'll also notice that it'll have a line up at the top and a line at the bottom that's completely connected from the top to the bottom. So normally what you'll do is you'll put your power at the top So let's say you've got 5 volt battery. You'll put the plus 5 volts up here, and then you'll put the ground down here. And so if you want to go to 0 volts, 0 volts is here, and here's 5 volts. And then that's how you can then wire up your system. Now, to give you an idea of what one of these things looks like in real life, here is what one looks like in real life. Okay? So what you'll notice here, and this is a standard type of breadboard, okay, is that this line at the very top here and the line underneath it, they are all connected. So what I'll quite often normally do is I will wire from like one of these powers to this top row. And then anytime I want to power something, I can put it there. And then I'll make this my ground, okay? And usually if it's a metal one like this, like you'll notice on the back here, the ground is actually attached quite nicely to all the metal. So I can actually clip on the side on the metal anywhere here, and all of this is grounded. But then the other thing I'll do is I'll normally tie a wire from here to down to here to make this my ground. So therefore I can always get to a ground. Then I take something like this resistor. Okay, so you see this resistor? And I can then put the resistor into the holes as shown here. You can see it sort of in the holes. And I can make it very easy to now attach multiple things to that single resistor. Okay? So if I look at this, everything that's in this one row or this one column here, these 5, if I click in anywhere, it's the same as attaching it directly to here. And the same for this one down below. If I wanted to put 2 resistors in parallel, I get the second resistor. I put it in. Okay. So now you'll notice that this one resistor here starts here, goes through the resistor, goes into right here, into that row. And so these 2 resistors are actually connected right here, and then it comes over here. So these 2 are in series. If I wanted to do them in parallel, I could easily just move the resistor over that way, and now those 2 resistors are exactly in parallel. And as you can imagine, it's real easy to clip on and measure voltages. Now, keep in mind, one thing is that when you're measuring resistance, sometimes you have to pull the one resistor out to measure the resistance, or else it measures it in parallel. Mr. D, did that answer your question? Oh, very good. Okay. Next question. Did it make sense about how to combine parallel resistors? Good. And did it make sense about how to combine series resistors? Good. And you probably also noticed that the practice really went into what do you do when you got parallel and series circuits in place. And honestly, that is the majority of the circuits you'll be dealing with. So if I come over here, and I'm going to go back to what we had before. If I come here and I look at practice number, this was the one that we just did. So in this particular case, you always look and you see what can be easily combined. So in this particular case, if I wanted to find the entire R equivalent facing the 60 volts, what elements are easiest to combine first? Any ideas? Which of these resistors would be easiest to combine? Any ideas? The three resistors in series, the 220s, 25, 25, 100. So the 220s actually would be fairly easy to combine because they are in series. These four are connected, so they're a little bit tougher. I tend to agree with the folks who said to combine these three, though, first. Because if I combine these three in series, the 25, the 25, and the 100, that's 150. Now I've got 150 in parallel with the 40. I can do that, and then I put it together with the 20, the combination of the 40 and the 150 and the 20, and that's how I would do it. But that's a very good point, okay? The 220s, though, Mr. Patel, don't feel bad because they can be combined because they're both in series. It's just I usually like to take care of the complex stuff on the inside first. But however you combine it, however that makes sense to you is good. Also keep in mind, a lot of times it really helps to redraw the diagram. Redraw the diagram in a way that makes sense for you. Okay? So let's look at some more issues here. Let's see. So in this particular case, which two are best to combine first? Should I combine R1 and R3 first, R1 and R4, R1 and R2, R2 and R3, R2 and R4, R2 and R1? Any ideas which ones you should combine first in this particular case? Of course, if you look over here, you'll see how I did it. So, oh, you can't see it. Okay. I'm so sorry. Is that better? I see R1 and R2. Okay, so combining these two first and these two, it really doesn't matter which one you would do first, but in both cases, by combining the two in parallel and then combining the other two in parallel, and then you'll have them in series, that'd be the easiest way. Again, you try to look for which ones are strictly parallel or strictly series. It's a very good example. We just did this example. Now, keep in mind, one of the shortcuts is that if all the items in parallel are the same, you can just divide by the number that you have there. So here we've got three 3 kilo ohm resistors in parallel. That's the same as a 1 kilo ohm resistor. But keep in mind, in parallel, it'll always be less than or equal to whatever your smallest value is. So in this case, I shorted it out. So therefore, the equivalent resistance to this is 0, which is a very bad situation. Okay? And then we talked about impedance matching. And this right here is one of the very, very important items that you should have in your binder, which is you should know how to calculate power is equal to VI or V squared over R or I squared times R. So that should be on your equations list right up there, right after V equals IR. So in this particular case, this is a very simple case. all the resistors are 100 ohms. So which two should we combine first? And by the way, if you're having problems reading this, you can just open up the in practice quiz. Any ideas? Can you go over? Okay. Well, let's do this one first, and then I'll be right back to that question. I heard let's see, one was R2 and R3, and one was R1 and R2. Well, R1 and R2 would be sort of tough because they're not either series nor are they parallel. Okay. So the easiest one is do R2 and R3, but because they're both in parallel. Here's the neat part. R2 and R3 are equal to each other at 100 ohms. So 100 ohms and 100 ohms in parallel is equal to what? 100 ohms and 100 ohms in parallel is equal to what? You should be able to do this without a calculator. 50 ohms, that is correct. So 50 ohms. And now I've got 100 ohms and 50 ohms. What's that in series? $150, that's correct. Now you notice we did that without a calculator. Later on, you're going to be able to design circuits to have a specific resistance, okay? And so just remember those rules about putting things in parallel like that, okay? So if I've got 15 volts and 150 ohms, what's the current coming out of the battery? What is the current coming out of the battery? Well, V equals IR, so I is equal to V divided by R. So that's 15 volts divided by 150, which is 0.1 amps or 100 milliamps. Okay? Now, the current through R1, since it's got nowhere else to go, it's going to be 0.1 milliamps here. Now, what's the current back inside the battery? Well, it's going to be exactly the same thing, 0.1 amps, because it's going to split the current here, but then it's going to combine it back. The power through everything is equal to V times I, which would be 15 volts times 0.1, which will give you 1.5 watts for the entire system. Now, next week, we're going to talk about, since this is 100 ohms and this is 100 ohms, I know that it's equal amount of current is split through these two. So therefore, this 0.1 ohms, I'll have 0.05 ohms going through here, or excuse me, 0.1 amps, sorry, going through here. I'm going to have 0.05 amps and 0.05 amps going through here, combining again to give you 0.1 amps coming back into the battery. But that's next week. Okay. Now I'm going to go back and answer that one question that we just had. Hold on a second. Okay, hold on a second. Somebody had asked a question about power right before we did this problem. Could you please repeat the question? Because I can't seem to bring it up. Wait, I can do it now. Can you go over how to find power dissipated over a resistor in different scenarios? Okay, so power is equal to V times I, or power equal V squared divided by R, or power equal I squared times R. Okay? Those three equations. So whatever's easiest for you to know. Is it easiest for you to know the voltage and the current? Is it easiest for you to know the voltage and the resistance? If it's easiest for you to know the current and the resistance. What you'll find out is that usually a lot of times you'll know the resistance, okay? So if you know the resistance, you're looking for which is easier to know, the voltage or the current. Whichever one's easier to find, that's the one you use. Okay, can you go over, let's see. And then the next question is, are they used over 2 points on each side of the resistor? Mr. D, I did not understand, is what used over 2 points? I didn't understand the question. Any other questions? So, okay, so we're going to go back to like what I need to find the voltage across the resistor. If that's the easiest thing, then sure. If I'm looking at this, since they're in parallel, I probably know the voltage a lot easier than I know how the current is split. So V squared divided by R is a much easier thing for me to do. If they're in series, they're always going to have the same current. Current's probably going to be easier for me to know. But sometimes I know the voltage and I know the current, but I don't know the resistance, in which case I use VI. So it's whatever's easiest. With impedance matching, why does the source impedance have to match the load impedance for maximum power transfer? Well, try it out. What ends up happening is that if you have lower internal and source impedance, what will end up happening is that you end up not how can I put this? What ends up happening is that the way the current, the way the voltage is split is such that that you're not going to get as much of a power transfer. And then if you got too much voltage, then you're keeping too much of it internal. And again, this mainly comes up in cases where you're trying to design a driver circuit. Okay. So if you can find the voltage across a known resistor, well, if it's a known resistor, like I can look at this resistor and by the markings, I can tell you what the resistance is, or I can measure it with my multimeter and determine what the resistance is, and then I can usually measure the voltage. So V squared over R is used a lot. But at the same time, if I know what the overall voltage is and I know what the entire equivalent resistance is, I know what the current is. And so a lot of times it's easier for me to just say VI. Again, whichever one of the equations is easiest, that's the one you use. Okay, next question. All right, did everybody have a chance to do homework, the homework page on combination circuits level 3? I hope you did. Good. Now, once you're able to do level 3, you really don't have to do level 1s and 2s. I mean, you can do level of 1s and 2s, but once you're good at 3s, you just keep going to more and more advanced ones. So you go to level 4s, you go to level 5, et cetera, et cetera. In fact, the homework for next week is to do level 3, 4, and 5. Okay. And the number one thing that you're going to want to learn as we go to more and more advanced circuits is the first thing you do is you simplify it for you. Okay. The way I might think something works really well is different than how you might. And in fact, you'll find that some people are just inherently better at looking at circuits and simplifying them. So you find out what makes it simple for you, and that's the correct way to do it. And even if it's slightly different than the way somebody else does it, if it works every time for you, try that. However, if you're really getting frustrated and you're having difficulty, get together with somebody. And in fact, you can even ask questions here. As you practice, you'll learn how to simplify it for yourself. Okay. Now, you will remember from the homework assignment from the slides, I included in here all the key, Ohm's law, Watt's law, series resistance, the tricks, if you will, the parallel resistance and the tricks. Remember to combine parallels and series resistance until you get back to 1 R equivalent. I cannot stress that enough. Okay. The more that you're able to practice combining circuits, the better off you'll be. Okay. And believe it or not, by the time we're done here, you'll be able to combine virtually any type of circuit imaginable. Okay. Are there any other questions? Are there any changes we need to make to the slides or to the live chats that would make them more useful? Are those swords or lightsabers above the whiteboard? Those are actually this is my sword and scabbard. I'll show it to you from when I was in the Air Force. I was an engineer for the Air Force for 5 years. That's where I got my master's degree in electrical engineering. And I did computational electromagnetics. And when I graduated, my parents purchased it's a ceremonial Air Force officer's sword. And it's usually the first thing I hang up because I was very proud of getting my bachelor's degree from LSU. In electrical engineering. And then when I got commissioned and I was able to serve the country as an engineer, it's really been one of the high points of my professional career. Thank you for noticing. Are there any other questions? Any electrical engineering or circuit related questions? Okay, so well, the thing is that I want you all to know, no matter what you go into in science, engineering, medicine, any type of field, you never know where it's going to take you. That's why you try to learn as much as you can, because you never know what you're going to be really interested in. You never know what you're going to be really good at. All of you are really good at science. You wouldn't be able to do science Olympiad otherwise. And so none of this is wasted effort. Even if you determine this isn't what you want to do, that's important knowledge to have as well. Now, next week, we're going to start talking about magnetism. And so we're going to be breaking out the magnets. And we're actually going to be talking about refrigerator magnets. Okay. And we'll be breaking out compasses. I will tell you, be very careful when one of the things I do recommend is to get a compass, okay? But be very careful with your compass and keep them away from other magnets. You don't want to mess up a compass's magnetation. Oh, binder check. I totally forgot about binder checks. Thank you, Mr. D. Okay, let's do binder checks. Everybody should have their binder, and I want you all to type in when you're able to find these items in your binder. I'd like everybody to find rule 2D in their binder. Go. Okay, what was it? What is Rule 2D? That's right. You're allowed to bring your own multimeters for use in place of the provided ones at the discretion of the event supervisor. So, if you're really good with a bench one, you can probably bring your bench one. However, I will tell you, those things are notoriously a pain in the neck to carry around. But if you have one that you're very comfortable with, bring it. I would recommend that if you bring your own multimeter, like let's say this is my multimeter here, make sure that it works, okay? You may still have to use the one that they have, okay? And I would also bring clips. And the reason why is that it makes it real easy to clip and test things. But you might know how to use this one a little bit better. So you're allowed to. However, if they've got the multimeter set up a certain way and they want you to use that multimeter as part of the hands-on experiment, you may not be able to use it in that particular case. Okay, binder check time. Show me Ohm's law. What is Ohm's law? You can't write it in until you find it in your binder. Go. Very good, very good, very good. Okay. Now, okay. Okay. Binder check. When was Nikola Tesla born? Go. That's correct. 1856. Anybody got a date? He died in 1943. That's correct. In fact, he died quite broke. Poor guy. So, according to this, he was born July 10th, 1856, died January 7th, 1943. Okay. So, again, that was a very good set of questions. Okay. What is the power equation when you know voltage and resistance? Find it. Go. Now, if you don't have it, then say, I don't have it. And that's fine. Because guess what? We're not in competition. There you go. All right. Mr. D did it right. I said you have voltage and resistance. Okay. And Mr. Dassey, that's perfectly fine. But guess what? It won't be fine next week. Because next week I expect you to have it. I expect you to have all of those items in there. Okay. I expect you to have the printouts in there that tell you how to use the circuit breadboard. If you get a chance to use a breadboard, I would practice with one. I would practice setting up parallel and series circuits with it. I would practice attaching batteries to it and then measuring the voltages. Okay? Because it's just a really good idea. Because a lot of times for the hands-on activity, they'll just give you the breadboard and they'll say you can't change anything, but you can measure voltages. And then they'll expect you to read the resistor markings off of here to know the amount of the resistance. And then you measure your voltages. And then they'll ask you questions about how much power you've got. You've got V, you got R, so you know it's V squared over R. And then they'll ask you, like, what's the current? And you know it's V divided by R. Okay? Okay, so with that was your binder check. And by the way, can I give you a little secret hint about how I figure out what I'm going to do for a binder check? I go to the rules. And when I go to the rules, I'll always ask you the first binder check question will be on the rules. So that was 2D. The next one will be Ohm's law. It'll always be Ohm's law. After that, I'll probably ask you a historical question about one of these guys. And by the way, right now, I am only asking you very high-level questions about Volta, Ohm, Tesla, Hertz, and Faraday. I will start asking you very specific and hard questions about them. And some of those folks, they did more than just the electrical stuff, especially like Michael Faraday, the stuff he did with benzene. So you have to be somewhat careful because there's a lot of stuff in there that you got to put off to the side. Probably won't be asked. Not a bad idea to have it there, but it has nothing to do with Circuit Lab. Do we know everything from the electricity part of the event from the presentations we've done so far? No. Okay, because let's look at this. We have yet to talk about, we've yet to talk about AC characteristics, okay? We have talked about most of this, but we've not talked about magnetic poles, electromagnets, transformers, motors, generators, the right-hand rule. We haven't talked about electrical control devices like three-way light switches, like the type of switch that you have with the light at the top of the stairs where you can turn it on and off from either the top of the stairs or the bottom of the stairs. That's called a three-way switch. And that's going to be a big part of what we're going to talk about. We have not talked about how LEDs work. In fact, I got to go down to the hobby store and buy a bag of LEDs because we want to really be able to make sure you understand how to use those. And the reason why they like using them is that, honestly, they're cheap light bulbs that don't break, but they are light bulbs that only work one direction. Okay? Now, we'll start getting Division C stuff actually in about a month, and then we're going to be talking about Kirchhoff's voltage laws and Kirchhoff's current laws. Now, we've sort of talked about them now in the way that we've gone around a loop and notice how all the voltages equal each other, and they all, as you go around, the voltages are always the same, and that's Kirchhoff's voltage law. We've talked about the current law in a general sense because we talked about if I got an electron going in, I got to have an electron coming out, the marbles in the tube, okay? Kirchhoff's laws will help for Division B. And in fact, for my Division B students and coaches, I recommend staying around for some of that stuff that we'll be talking about this Division C. I actually disagree. I would have liked to have seen Kirchhoff's voltage and current laws within the rules for B. I totally understand why they were not included, and I completely support the decision. But I just think there's just such a key element for it makes life a little bit simpler, and it helped me understand how electricity worked. But we're also going to be talking about RC circuits. We're going to be talking about the electrical characteristics of a silicon p-n junction. That is not, there's nothing in there that's useful for Division B. And then, of course, we'll be talking about operational amplifiers. And again, that's Division C. And I will tell you, it's one of my favorite topics. It's probably the one I'm most looking forward to discussing. It's not of any use to anybody in Division B, though. Okay, any other questions? Okay, and remember, you can send me emails if you have questions. Some people have been sending emailed questions, and I have found 3 errors in practice number 5 slides. So I fully expect that's going to be one of my first questions: is what are some of the errors in the practice 5 slides? So when you look through the practice 5 slides as they are written, there are errors. Okay. And I want you to look at them and see if you can figure out where they are. Okay, last call. Any more questions? Okay, everybody, have a great weekend. Practice 5 has already been posted on the YouTube channel, and I will be working on practice 6. We upload corrected slides put on the website? Absolutely. All right. Well, take care, everybody.